Hello everyone and welcome back to another video. Today I'm here with Existence University to just talk about some physics, talk about whatever comes up as well. How are you doing, man?
Oh, pretty good yourself.
Doing pretty good. What have you been up to today?
Just kind of working on this video for quantum and objectivism. Part of like a three-part series thing.
Yeah, that stuff. A lot of objectivists are not big fans of quantum physics, but
Well, they have good reason not to be, I feel.
why do you say that?
Well, I actually just watched your last video. Came out like 23, actually at this point 24 hours ago.
Yeah,
Uh, and where you say that like some of the kooky theories, you know,
yeah,
about
yeah.
quantum mechanics, like or just not even the ideas that might come from a scientist, but the ideas that come from some pop journalist writing about the thing. Just like when uh, something from biology, it's like, oh, chocolate cures cancer. But if you find the study they're talking about, they found an enzyme that is in chocolate killed a type of cancer in a rat. Like it's so
Yeah,
far, like, and it's the pop science is the same thing to all those things. And I think there's good reason to be a little standoffish.
yeah, for sure. Especially yeah, with a lot of the methods that people use in science, like people will just adjust variables to get like surprising conclusions and stuff like that. And just like a little adjusting of assumptions can lead to massive changes in results. I was talking with Fate Crowder the other day about how like I had like an actuarial science like case study, and like we changed, like each group got like completely different results for our final answer, like going from like 50, increase rates by 50% to like decrease rates by 40% just because of a few changes in assumptions. Um, so yeah, like just the assumptions that people make with studies can lead to all sorts of crazy results.
Yeah.
And
Check your premises.
yeah, check your premises. And it seems like a lot of scientists have bad premises coming in. That leads to all sorts of terrible interpretations, I guess, of quantum mechanics. Like I know I sent you that Matthew Santoro video where it was just all mystical bullshit and
Yeah.
those sort of interpretations of quantum mechanics. But the thing is, like the quantum phenomena, like from my understanding, they're real. These are real facts, so we can't dismiss them altogether just because certain people have terrible conclusions from them.
Yeah, it was like there's experimental results and then there's the interpretations. And
Yeah.
so, even in the way you do certain things, like I got in an argument recently about like the uncertainty principle, but the uncertainty principle, it's not about quantum actually. It's about any type of wave. And it's like the way you think, or the way a wave is. Like if you know what a sine wave is, right?
Yep.
And a sine wave goes in both directions infinitely, and it always just repeats.
Yep.
So it's like if you were to say, "Where is the sine wave?" Well,
Oh yeah, that makes no sense.
it makes no sense of a question. And so if you're talking about a photon and you're saying a photon is a wave, where is the wave? And it's like if you're talking about it traveling and it's in its wave state, you can't really say where it is. But if it's got a wave, then you can find its momentum. That's the other thing you can do with a wave. And you can use the full infinite sine wave to discover what a momentum is. So you could say, oh, the moment we know what its momentum is, we can't tell you where it is because it's a sine wave.
Yeah.
But if the photon hits something like your retina or the camera that's detecting it, the photon is absorbed, like all the energy is absorbed, so you know exactly where it is. But if it's been absorbed, if the photon's been absorbed into a single point, there's no sine wave anymore. So what's its momentum? Well, it doesn't have one. And
Yeah.
so it's not about measurement, it's a physical limitation based on the fact that you're talking about a wave, and then you have to look at it from two different ways. And when you turn it sideways, you kind of get a one-dimensional look at it. You turn it the other way, and you get a 3D wave all the way, or like a 2D wave. So it's kind of like looking at the graph of a sine wave sideways or side, like you
Yeah,
get two totally different responses.
yeah, for
So it
sure.
looks contradictory, but it's just in the way you're talking about it. So it's like the experiment comes true that way. But
Yeah,
now when we interpret what is a photon, that's when things start falling apart.
yeah. So I guess that, yeah, photons are tough to define because they, I don't know, from my like high school physics level, like we talked a little bit about it, and it's like they behave both like a wave and a particle from all the experiments that are done, and yeah, that I
Yeah.
mean that
And I
makes.
think then the best way to what you do is it's not a particle and it's not a wave. It's
Yep.
there's no duality between
Yep.
when it does this and when it does it is one thing and it's neither a particle nor a wave, nor is it a wavicle. Like Leonard Peikoff makes fun of the 20th century scientists for calling it a wavicle, although I've never heard anyone call it a wavicle
Yeah. Oh, you're cutting out a little bit.
except for like Peikoff. But okay, sorry. You want me to start back a bit or what?
I think I got most of it. I don't know. It cut out for a few seconds, and
Oh,
it's
just
something.
just like
Something talking about wavicles.
yeah, the Peikoff used that term. I just thought it was funny. I've never heard anyone else use
Yeah.
that. But it's not that either. Like what it is what it is.
Yeah.
What it does in experiment looks like a particle, and it can look like a wave. Like when you do the thing where like the double slit experiment, and you get the wave pattern.
Yeah.
That's what it would look like if you sent water waves through. So it's a pure analogy that it's acting like a wave because that's what water would do,
Yeah.
but it's not a water wave. So it's then going, okay, it is a wave because it has a pattern that's similar to a wave. It's like the fractal of a tree and the neurons of your brain are the same thing because the pattern is the same.
Yeah.
It doesn't, you're starting to give it something that it's not.
Yeah. So I guess yeah, we obviously need different concepts for these things. It's important to like recognize similarities, and like integrate these similarities and like form equations based on them and those sort of things.
Yeah.
But you can't say that those are the same thing because they look the same. That's pure rationalism. That's just
Yeah, it's
like, oh, I feel they're the same, so then they have to be the same.
Yeah, it's like the wave equation works to help solve things about the wave in the quantum world, but to say it is a wave is taking it too far.
Yeah. So one question I have, I've heard that like, or I've seen stuff that shows how like electrons can, if they're like shot a bunch, like behave similar to a wave. How does that work? Like through like a double slit sort of thing.
It's the exact same principle that of the photon, but through the idea that we have matter waves. Ooh, go down. So matter waves are just basically everything is a particle in a wave, and then dropping that we are neither one or the other. The thing is, the more observable you are to the universe, the more objective you are to the other entities in reality, the more your like position and momentum can be known. But the smaller you get, the harder you are to detect. Does that make sense?
Kind of. I don't know. It seems strange that electrons, like since like they're matter, that they would behave similar to waves. But it's possible that our whole like dichotomy of like particles and waves, that's just a bad dichotomy in general. Like
But
things are
who
just,
told you that electrons were particles?
I don't know. I guess I just always thought that might not be true then.
Exactly. And so when it's been discovered that they also have the properties of a wave. And so do molecules, and so do micromolecules. That's as high as so far as science has been able to test that micromolecules also have a wave.
So then it's possible then, I don't know, this might just be pure rationalism, but like everything is like there's no it's sort of just this range kind of like between waves and particles. Like particles
Well,
can behave
that's
like
why I
waves
say
or not. Is that
well,
just
that's why I say you
rationalism?
gotta. That's rational. using those concepts in a place that they no longer fit. Like the
Mm-hmm.
patterns show up as those things, but we can't, like, at least if we want to talk about them, we have to deal with the package dealings that the history of science,
Mm.
has put into them. Because it's like, if we just jump in, okay, let's talk about them like they're particles or like they're waves. If we bring in the 20th century, 21st century physics with it, then we're going to start just throwing out, oh, this guy said this, and
Mm-hmm.
so then you just start getting pulled back into the rationalism.
Yeah, yeah, for sure. So then, like,
I think,
what sort of theories are like used right now to sort of unite these without like saying that they're both particles and waves, and like this sort of like still subscribing to this like this past dichotomy that doesn't really work anymore.
uh, I'll give you three different kinds. There's like the two bad and the one that I think is the good,
Mm.
right? And it follows the same lines that when Peikoff is looking at philosophers or physicists of the past, or when like Binswanger is looking at conceptual thinkers, that it comes down to the subjectivists, the intrinsicists, and the objectivists.
Mm-hmm.
The subjectivists have the Copenhagen interpretation, which is like the Schrodinger's cat in a box. When you, a human observer, look into the box, you determine reality.
Mm.
They have this, it's the fragile superposition. So, like, a superposition is just probabilities added up.
Mm-hmm.
100% likely of the cat is 50% alive plus 50% dead. It's a superposition, right? So
Mm-hmm.
it's just literally adding probabilities. It doesn't mean, right? The Copenhagen thing
You
says
cut out a little
that,
bit when you said adding probabilities.
oh, that uh, where did I go from there? Or where did I
Sorry.
start from?
You were talking about the Copenhagen interpretation and saying that they just like added the probability, so it's like fifty
Well, it's
percent
like,
alive, fifty
I'm just
percent dead.
I'm going back a bit and just saying superposition
Mm-hmm.
is a thing in like classical mechanics and stuff too. It's just that, like, this plus this, this probability plus this probability equals 100%,
Mm-hmm.
right? It's like if you're holding a baseball and you don't know if you're in a gravity field, and like you let go of the baseball, it's either 50% going to drop or 50% going to hang. If you know you're on Earth, it's going to like 99.999% fall, and you
Wait,
know
why not 100%?
well,
Oh, you're cutting out now.
maybe at the moon, or like a giant planet. Maybe a giant planet flies overhead, and all of a sudden gravity shifts. But just like, or that, like, that there's a magnet and goes up. Just there's this error of probability. I was just making
Sure,
an
sure, sure,
example.
sure.
But that a superposition just means all the probabilities added up. The Copenhagen interpretation says it's fragile to human consciousness. If when we look at the cat, we determine if it's alive or dead. And
Hmm.
that's obviously a subjectivist
Yeah,
interpretation.
that's actually how I've heard someone describe like the Schrodinger's cat thing. Like they were like, "Oh, the cat's both alive and dead because it's in the box and we don't know whether it's alive or dead." And I was like, "Holy shit, you don't understand that at all."
Yeah, it's
That was my initial thought.
the superposition, the what are the probable states of that cat, alive or dead,
Mm-hmm.
come to alive or dead. Cat
Oh,
is either one or the other, obviously.
yeah. Yeah, yeah, for sure.
Um,
It's like
and
with anything. It's like with anything for probability. Like you have like the whole like let's say you have like a normal distribution and you have a random variable that adheres to that normal distribution. Like that distribution, that's like the true thing of like the variable is going to be one of those numbers, but the variable itself is going to be one of those specific
yeah,
numbers.
it's gonna be one of them.
Yeah. Mm-hmm.
Yeah. So, and then there's the intrinsicist view. They say that the superposition is not fragile at all. And when you make an observation and you find the cat is alive, the cat being dead can't be false because the superposition isn't fragile. And so the world split into two different worlds and every choice splits into many worlds, and it's the many world interpretation. They hold that every superposition is always true, and because intrinsic, like the superposition is intrinsic to the universe, so one of them can't fail. They all have to be true. So you get like an intrinsicist view of things.
Yep.
And then there's, I think, the man himself, I don't think is an objectivist, but I would say the objectivist view would be quantum Darwinism, which says that like the cat being in the box, the box itself knows whether the cat is alive or dead, because the cat is still breathing, which is putting pressure on the walls. That is, like the photons that are hitting the cat kind of know if the cat is alive or dead. Because the cat has so many different ways of interacting with the rest of the universe objectively sees the same thing. And so it's like when we look into the box, we see the cat alive or dead.
Yep.
Because it is alive or dead, because like probability wave, its matter wave is elapsed in interacting with air and the vacuum of space and the box and itself and photons and cosmic rays, that the universe is so packed with things that everything about like the universe knows about itself in a sense, so that probability is instantly known by the universe. It's like Stephen Hawking talking
by saying known by the universe, you don't mean like the universe itself is conscious of all this. Yeah, for sure. I just want to clarify for the audience so that like people don't in the comments aren't like, existence is saying that the universe is conscious. Is he a religious person? Because somebody would do that.
No, it's with the quantum Darwin, they've actually like they passed their first tests of like experimentally, and in that the universe knows. It's instead like it's kind of doing the Schrodinger cat experiment. Instead of looking at the cat, it talks, and like by time you get like 1% of the environment known to you, you like know 100% of the time what the position already is. And it's like you could get it would, and then it kind of plateaus out, and then it's like the last like 97% gathers that last bit of information that doesn't really change anything. But it's just that like the moment you kind of look at just a few photons that passed by the thing, you can look at those photons and they hit the object and reflected off a new color. So if you see that photon that went from this color to that color, it interacted with something. So it's like you can get the information that the thing exists from the environment around it. And so everything in the environment can get that information about that thing. And so you get literal objectivity out of that.
For sure. I'm trying to think of it. Like this is somewhat complicated stuff, but I think I kind of understand it. And like all this is basically the uncertainty principle, right? Or how that's what we've been talking about, correct?
It's kind of like measurement, basically.
Yeah, how we can measure these things.
Yeah, and it's like the subjectivists say humans measure it. The intrinsicists say you measure one of many universes because they all exist. And the objective view is the universe kind of takes its own measurements.
Yeah, so like everything. Oh, you're cutting out.
Yeah, you're cutting out too.
Yeah. So like it kind of just shows like everything's like connected. So that's how we like can know certain things about like these photons, even though we can't like directly observe them.
Yeah, it's if you think about it maybe as like walking through the snow, or like what is measurement? And like you have a meter stick and you drop it in the snow, you pick the meter stick back up and walk away. Someone else can walk past and go, "Oh, someone dropped a meter stick here." It's like, how do you know? Well, it is a meter long stick in the snow. Yeah. The snow has observed the meter stick as a meter long kind of thing. So like, but the meter stick's made up of an infinite, or not an infinite, but a giant amount of atoms and electrons and protons. which we know at this point are waves, or what, or mostly empty space, or whatever you want to fantasize about the
Mm-hmm.
particle. It's a meter stick's made of a bunch of tiny, tiny particles. That should be quantum. But when you drop the whole meter stick in the snow, all of the quantum particles of water, all along and they all know each other because they're all touching each other.
Mm-hmm.
And it's just that the meter stick's a meter long because everything in the universe observes it that way.
Hmm.
Well, not everything,
So
because
how's
there's
that
things that
like?
are going to be too far away.
Yeah.
But
Is there like a probabilistic nature to these things, or like if something, if like I don't know how to explain this, but if something's like,
I don't. I know what your question is, and I don't know how to word it either, or how to
yeah,
really answer it either. But it's like uh, it that there is a probability, but that it is so instantaneously known by everything in close proximity to it that if it's larger than a single unit, that basically everything knows that that thing is an entity around it, at least. That it kind of leaves a footprint on everything because it interacts with those things.
yeah. So like that's, I guess that's how like the universe can follow cause and effect and be like a causal universe, even though like the smallest things like can behave
Yeah,
probabilistically.
yeah. It's actually the thing I'm talking about with quantum Darwinism is called redundancy. So it's like, say the molecule's got 5 different probabilities, right? But 4 of them, they interact with the universe in some measurable way, but like 1 instance each. And then one of those 5 hits like 7 photons in the area. And
Yeah.
the information of like the 7 photons say, oh, it was like this. It was like that one of those 5 probabilities. Whereas the other information is kind of lost and turned into heat. And then, but all of the other information has a copy.
So
And it's called a redundancy.
what do you mean by information in this context, or just like the things, or like what we know about the things that are happening?
Well, let's do an example of, like, say, color, because color is part of a photon and can interact with big things. Uh, when, say, white light, pure white light, or maybe every wavelength of light at the same time hits you, the visible light will like bounce off, like be absorbed and bounce off you, right? And what it does is it's actually just it excites an electron. The electron goes up, kind of. This is a Bohr model, which is a jump level, and then when that energy, at some point, probabilistically in a sense, falls back down, it shoots off a photon of a certain color.
Yeah.
Right? And so that photon of a certain color has information about where it came from. It came from an entity with that energy gap level, which corresponds to humans as a color.
Yeah. Yeah, for sure, for sure. So like that just tells you like where the electron's at. Like it tells you like if it goes down from like the second energy level to the first, and it's like this distance or whatever, it releases this color of light, so you know that it's on that energy level.
Yeah, you know where it is because which direction the photon came from. You know the color of it, which is the energy level. And it's like if you get enough of those photons from a similar area all coming at you, like what your retina does. Say, in taking this all the way, it's like you get one photon hit your eye. That's just a sensation, and you lose it because it's not a percept. It's not
Yeah.
retained in memory, right? And it might not even register to your eye because it was just one,
Yeah.
and it wasn't enough to actually get the percept. But then when you look at any object, you're not getting a single photon. Like, there's no way for us at our scale to look at any object and see more, like less than 1 million photons hit us, kind of thing, right?
Yeah.
1 million things all containing the same color,
Yeah.
coming from the same direction, that's a redundancy, you know. And when it hits us,
Yeah.
our eyes kind of recognize the redundancy. We recognize that all of these photons all have the same color because they're all coming from the same object. And all of those photons are what's telling you there's an object there because they measured it first.
All right, for sure. Yeah, yeah, yeah. And then the probabilistic thing is with the whole electron, like which energy level it's going to be on.
Yeah, it's like when it falls back down, there's like, how do you know? And that's the same
Yeah.
with like nuclear decay. When it's when it decays, how do you know when it, you know? But
Yeah, and that's sort of like just almost random or not random or just
I I wouldn't say random, and I wouldn't want to bring probability.
yeah.
Um, but that's that's where I stop, right there. Right
Yeah.
at this moment, that's where I'm kind of stuck myself
Yeah.
because it's like, yeah, well,
Oh, you're cutting a little bit.
it's kind of Einstein's hidden variables. It's kind of like Einstein's hidden variables is what, you know, like, is there something that we're just missing? But that's been shown wrong by Bell's theorem. And so that's what kind of quantum Darwinism fits in, where it just kind of says, well, the best way I've heard it, the guy that made quantum Darwinism, the way he said it, was that like all these other interpretations are concerned with like just the system and the thing it interacts with, like the object, like the particle, and like the camera. It's like, but they forgot to incorporate the rest of the universe around it, you know,
Yeah.
and they're looking at something that's just one part. And so that like the hidden variables are kind of in every, like all the other probabilities kind of take place, and I guess, but off of one photon that dies or like, you know, turns to heat, it doesn't really become redundant information. But I'm not entirely sure about that.
Yeah.
That's just kind of me speculating and talking off the top of my head about it.
So then we don't really know how to determine what energy level that a photon is on, or that not a photon, an
No,
electron is on at any time, or
no, we know how to detect what level it's
oh yeah, yeah,
on,
yeah, yeah, yeah. But like we
but
don't know.
not when it's going to go back down,
Yeah.
because it just has kind of fuzzy energy, and then it at some point will release. Maybe it has to do with interactions with uh, the little stuff that's where nothingness is not. That's Ayn Rand's little thing about
Uh.
the universe for being full.
Yeah.
Like, so maybe it interacts with that, you know. But at this point, I am not obliged to say because I have no idea.
Yeah. Yeah. For sure. So it sounds like there's nothing really like probabilistic about any of this. If this can be like explained through just things like the electron
Yeah,
just emitting things, it's all just
yeah.
objective, just
I
cause
was
and
just
effect.
yeah. I was watching one of the quantum Darwinism lectures the other day, and he went through his axioms, and he's getting them from a textbook, and he stops too short, and he goes like, these two lead to probabilities, and he's like, we don't need them, and he's like, we just, and he's like, but he still comes up to those axioms without probability using the ones he had, so he still gets all the axioms he needs, but without using the old-fashioned way, which introduces probability. And he's like, no, we don't. Even people that he like had like an open question period, and that moment people just started asking so many questions. He's like, no, like he just kept throwing it away. He's like, no, we don't need it. He's like, we don't need probability in this. It's
Yeah.
just kind of like that information exists and is lost because it's not redundant, because the universe sees the object as objective, and the information it sees is the information that, it's the reason it's called Darwinism, the information that spreads its information the most is the winner, kind of thing.
I so like what is the wave function then? Because that's doesn't that introduce some sort of like probabilistic thing about the location of a particle, or am I do I not know what that is?
Well, yeah. So, well, stepping back, it's like the wave function is still like if we do the experiment where we send like a particle, like even an electron, through this machine, it will
Mm-hmm.
go like one way or like it will. The double slit experiment is the best one
Yeah,
actually,
yeah,
the one everyone knows. Like if you send it just through one slit, you kind of get that bell curve of probability,
mm-hmm.
and that's where the probability is introduced. You're taking not one photon, and like you are taking the millions you shot at the wall and
Yeah.
saying overall all of these photons show a probabilistic nature.
So then, why do some go like to one spot and then others go to a different spot? Like, why is that the case if they're
Well,
like? Because doesn't the double slit thing apply to with electrons? Because I've heard experiments where that's been done.
yeah, the in both cases it's still like that's what we were talking about, like that it acts like wave. But then I think I haven't ever thought about it with say quantum Darwinism, so let's ballpark it here. That if something like an electron or a photon has probabilities, and the one that survives and reproduces its information to the environment the most becomes the object of objectivity to the things around it, then the information, say one electron passes on, is that it's going at a 30-degree angle rather than straight on, and the information it passes on is in that direction. But the the thing itself, or like every single one of them has the probability to go either 30 or 45 or negative 30, or like you just kind of, so if it's got this scale probability they can go between, that's the whole
Yeah.
system can go between, and that each electron gets one choice,
Yep.
and that choice is shared to all of the little stuff it flies through. So every little stuff of the universe knows that electron has, say, collapsed to 30 degree, like to a 30-degree angle, and then like the next one, the entire universe knows it's going at a 45-degree angle.
Yep.
But uh, when you take like 100,000 photons are going through this experiment, and they all have a probability of going in one of those angles, then it's like, oh, then they have a probability of being in all of these spots at once. Well, no,
Yeah.
the
Yeah.
entire system has a probability of being all at once. If you shot them all at the same time and the universe still put them all in their same path, then yeah, they would all hit the wall at the same time. You're taking a whole system, the probability of an entire system of things, and then trying to apply it to one object. It's like saying human beings, there's a probability of what a human being will do for their career. Therefore, this one person has a probability of being a plumber today and an astronaut tomorrow. It's like, no, that's not how that works. You can't apply the probability of what humans will do to one human. I think that's kind of what they're doing to in that case of that interpretation. They're saying the probability of all of these photons can do different things. Therefore, this one photon does all of them.
Yeah. 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 For sure. So this might be asking a question that you might have already answered, but like, let's say like, how can an electron that's going at like this one certain speed, certain place, no other variables changed, behave differently than another electron doing the same exact thing at like the same speed, same distance, same place, same like all those other sort of things?
I think that's where the probability is, but that the universe kind of instantly, like once it's figured out, it's figured out. Like I can actually send you after we're done here um, a graph that kind of shows how quickly the information is known. But there's this small, tiny little gap at the very beginning of like a few microseconds that it doesn't really know what the thing is. but once it takes in like 3 or 4 photons and says like what color were they, basically, then it's like, oh, once like 3 or 4 are known, it's like, oh, okay, it's a blue thing, and like it kind of goes off and says like, ah, oh,
Oh,
it's classically now. But that you just need a few particles, I think. But if you haven't measured those few particles, which already have the information, then you still don't have that information. There's probability in there.
yeah. Let's say we shoot one electron at the double slit. Is that
Yeah.
like, do we know which way it's going to go? Can we determine that, or is that going to behave probabilistically?
It works in the same way as the double slit, except that the probability that we know is like the IQ bell curve. Just a single bump. But it's still within a bell curve. It's still somewhere, maybe not much over here, not much over here, a lot in the middle. But it's like we don't know where it will land until it lands, because we can't really observe it we can't observe it without destroying it. And the back wall is what's destroying it.
So would that be more of like an epistemological error or a like metaphysical probability? Like, does it do this because we like don't know enough information about it, or does it do it because metaphysically it is probabilistic, like in its nature?
I think the second one, but the problem with all of those words is all of the package deals that currently come with them. It's like, I think that's a correct analysis, but if you instantly then jump and Google all of those words, you will get the wrong idea.
So like what sort of
what they're trying to.
What sort of idea would I get that's different from like what's the package deal that is sort of going with that? I guess I don't that might be asking you to unpack a lot here, but
well, give me what was the line?
What with the probabilistic?
Like yeah. Well, there's probabilistic in the first place, which say comes from Laplace doing gambling math for the royals. Like, probability was invented so that the royal family would stop losing money when they gambled, because they didn't understand what odds were. So when Laplace started probability, he came at it from a subjective point of view where you aren't supposed to know all of the cards.
Yeah.
And so like the study of probability comes with card games. And so then tying what it basically is the math of card games to the universe and fundamental particles, like there's a package deal in there that doesn't quite fit.
Oh yeah, so like a package deal between like pure randomness and like not knowing anything about this, and like knowing like that there's a set probability. There's like this set like PMF, probability mass function, or whatever the word is. Like there's a set sort of probability function that we know, kind of. Is that?
I'm not certain. I'm not certain with the wording.
So like the false, I guess the package deal is like packaging just like the randomness of a card game with with like
the subjectivist nature of it too, because like doing the math in such a way that you are a player of the game, and then applying that to physics where you're trying to like be the game and try to, how can we know this from all points of view, but you're coming at it from a point of view of a gambler at a card table. And so you're saying, oh, well, we don't know it, so the universe don't know it. But like if the table that you were playing at was made of glass, anyone underneath would know instantly what the probabilities. I was kind of thinking that like if you watch online, or like if you watch the World Tournament of Poker, to the people playing there's probability, but to you at home you already know who won. There's no probability to you. The cards are known. There's still a little bit, because there's still a deck of cards that isn't fully revealed to you, but to each card to each card in the deck, they know, if they could know, they know who's on top of the other one. The universe already has a stack of cards.
So like I guess then the universe, like metaphysically, this it's already known when the particle hits there where it's going to go specifically. But for us, we can just choose say like, oh, we don't know, so there's like a probability it's going to go here, or probability it's going to go there.
Yeah, and like that's where the waveform really came in. Like when they were, shooting it through one thing, oh, shoot it through two things, we're going to get two bumps. And then they didn't get two bumps. They got a wave pattern. So then they went, okay, it's a wave, and kind of that's end of story. It's a wave now. And so you get the certain pattern, but it doesn't. You can't fully apply it like that.
Yeah. So
Like,
wait, does that mean
to
it's more? So does the probability more come from an epistemological fault then, or is it like a fact of metaphysics that these? I guess I'm asking the same question, but
I think it's we've come back around to it properly. That it's both. That for like 99% of the interpretations of quantum mechanics is an epistemological problem about a metaphysical thing. That thing is that everything has like probabilities to it, including that like that you could walk this way or this way, and you can add them all up. But if you were always going to be walking in a straight line, you walk in the straight line, then you go, oh, I was 100% right about going straight. Like you've always got the option to go a different way. Or with with small particles, they have, with interacting with other particles, they also have a way, an option to go different ways. But once the collision is made, they kind of have to know where they're going.
Yeah.
But to us, it's really an epistemological problem because we throw two baseballs at each other, and we're like, okay, we know what's going to happen. And when it happens, we're like, okay, cool. We throw two electrons at each other, and we go, it's going to act like a baseball, and it doesn't act like a baseball. And we're like, whoa, what's the probability of that?
Yeah. Because, well, electrons just have a different nature then in that sense than baseballs.
Yeah.
And we can't like apply the nature of baseballs to electrons.
Yeah. But I can do it in a small form of like talking about entanglement. Like because that's what is really happening when two things interact is entanglement. And if you could do it at the classical level with like baseballs. If you throw a baseball, it's got a probability, say 50% of going really high, but really close to you, and a 50% chance of going really far, but, it never gets very high. Right. And
yeah,
so
but
you don't know.
Like once you throw it or hit it, like it's going one of those directions.
Yeah.
But with the electron, like once you, like with the double slit, once you shoot it, do you know where it's going to go after, or can you know where it's going to go after it's shot? Is it guaranteed to go a certain spot after it's shot from like the cannon towards the double slit?
No, not really. No, not really. But so going back to the example though, because I think I can get into that.
Yeah.
Is that like the baseball, and we're talking not metaphysically, but like epistemologically trying to solve a problem, that it has a probability of doing one or the other. And we just kind of stop time the moment it's thrown and go, okay, 50% chance that it's going to do this. We're going to do this. Kind of, have you seen or like America's Funniest Home Videos? They like pause the thing and make the audience pick which blooper is going to happen. It's like they stop it right at the moment, and then they go, okay, there's a probability of this, this, and this. That thing, like the ball going at the person's, head, body, or groin. And it's like, so that ball is in a superposition of those three things. And like, this is just for us studying it. And then you push play on the tape and it hits the, person in the head. And it's like, so it was always going to hit them in the head. They just paused the tape. And so our wave function collapses to the superposition is, it hits them in the head.
Yeah.
But if two objects were coming at each other and they both had those same probabilities of like head, body, groin coming from two different angles, but then the guy ducks and they hit each other, they become entangled. And really, like at the classical level, that's just, now we have to do a formula for which way they will bounce. But now there's a probability that one goes up this way and one goes down this way, or maybe this one goes down and this one goes up.
Mm-hmm.
So now there's a like superposition of their entangled state. And if you look at this one go up, you instantly
Yeah.
and that's that entanglement idea. That once you know one, you instantly know the other. And if you do
Yeah.
the same thing to photons, they is kind of acts in the same way. Except baseballs are so much more massive that they tell the universe where they are going a lot faster. The photon gets a few seconds of not being noticed by anything. It can avoid
Oh,
cosmic
yeah.
rays and other photons a lot better.
So like it just
But
doesn't
it's gonna,
interact with anything, so it doesn't.
yeah, for like a tiny fraction of a second, or a fraction of a fraction of a fraction of a second. But then
Yeah.
it's going to go through a cosmic ray or a neutrino, which won't even affect it.
Yeah.
But they do collide a little bit, and that tiny little bit of collision says, to the photon it says there's a neutrino. To the neutrino it says there's a photon.
Yeah.
And both of them are now determined by the universe.
Yeah. All right. I
That's at
think
least
I.
my interpretation.
Yeah. I guess I think I get it a little better. Um, it's just it's just things have different natures in this sense, and that leads to
Yeah, essentially,
different
yeah.
different sort of outcomes. I guess
And
that's
that
like the general
and
takeaway.
the
Now, like
that nature comes down to also how they interact with other
yeah.
things of other natures.
Yeah. All right. Yeah. So is that's kind of why we can't like measure this specifically without like disrupting it.
Yeah, well, it's like especially because we want to throw an electron or a photon, or like see like as small as we can get. So let's go to a photon and try to so it doesn't interact as much because an electron's bigger. It's going to interact with more things, and you try to throw it at something. Well, it's still going to interact with cosmic rays that are just raining down on us. It's going to interact with neutrinos that are raining down. Interact with
Oh, you dropped. All right. What were we talking about?
I was just saying that that you can't really isolate your experiment from the universe. So
Yeah.
in trying to like get the probability of what a photon will do with when it instantly is kind of known by the neutrinos and cosmic rays that it interacts with, since you can't take it out of the universe to experiment with, the universe will know it before it even hits the back wall. And if the universe knows what it is, it's an object.
Yeah. So like, but why can't we, or why can't we measure it?
Measure what though?
Measure where it's gonna go, like for sure. Like I know there's like some problem of measurement with quantum physics.
Well, it's not even necessarily fully with quantum mechanics. Do you know exactly where the baseball that you throw is going to go every single time? Even when you build a robot to do it, it's going to be land in different positions every single time.
Yeah, for
And so
sure. But like,
that's because it interacts with the universe. It
yeah,
has to go through the same air.
yeah. But I know with like the double slit experiment, like if you like look at how, or if you like watch, if you have an observer, it like changes the outcome of the experiment or something like that.
But I think that's just because they're getting tangled in how they're observing it. But
Yeah.
the
All
thing
right.
is, because when they move it, say to the front slit, the detector to the slit, that's when it like does its first interaction with an object, which is like the slit itself, and that's
Yeah.
where like say its decision to go left or right is made. And so it's like you have it at the back wall and you get a probability because they all had time to travel a certain distance. You move the observer right up to the front and you find that it's acting like a particle because it's like the thing you sent from the machine was a particle. It had interacted with the universe already and was determined as a particle.
Yeah.
The whole point of the slit was to kind of change it into something else by making it interact with something. You interacted with its nature to make it slightly different. It's kind of like being a lion tamer. And it's like you whip the lion to make it mad, and then you put the chair up to kind of calm it down. And then,
Mm-hmm.
The experiment is the switching of those two things. It's like you're turning the thing you shot out of like a cannon in
Yeah.
into a thing of that it wants to interact with. Then you get a wave. Then you just detect a wave at the back. You put the detector before you turn it into a wave, and you find it's a particle. It doesn't. There's no collapse or change of anything. It was decided like you shot it out of a cannon as a particle, and then you
Yeah.
detected it as a particle. You send it through something that kind of changes its nature, kind of just makes it like we were talking about the sine wave,
Mm-hmm.
that the slit kind of turns it sideways, and
Yeah.
so but it's coming at you at a straight line. The slit kind of turns it sideways, and what you measure are like its momentums or its positions because you shot a momentum, and what you get is position. So, but
Hmm.
the slit itself is kind of the changing of your perspective.
Huh. So like,
It's like it's a
how does
Fourier transform.
how does the slit specifically like change the perspective on the particle or the particle slash wave slash whatever? Like neither of the two.
Well, at this point, I would say A is A. That's what it
Yeah.
does. Like
Yeah.
that's what we know of it. When
Mm-hmm.
we do the experiment, that's what happens. I don't think anyone's got an answer for that yet. I
Yeah,
think
for sure,
that's
for
part of
sure.
its nature.
Yeah, for
So
sure.
it's like
Yeah, no, I wasn't
um,
saying like, oh, it doesn't happen. I'm just saying like
yeah,
why does that happen? I was just
yeah. Well, I just mean like that. There's no way for me to know if I've answered that question. I think
yeah, for sure.
like even if it's true one way or the other, I don't know if you could fully say. Not at this point.
Oh yeah, so it almost be asking like, I don't know, like why does an ice cube melt at 32 degrees? It just that's the way it is.
Yeah, so that's a part of its nature.
All
And
right.
it's like we just know when we do that, we change its nature. And when we change its nature, we can get this range of where it's going to land. But we lose its momentum because we've changed the electron from its momentum of being shot to, the position that we measure at the back.
Yeah.
And so
Wait,
it's
what do you mean by like losing its momentum? Like how do we not know how much like momentum it has
in
after
that
that?
just in that uncertainty because it's hit the back wall and it's been absorbed. And what are we talking about? The sine wave. If the entire sine wave is absorbed into the detector, what's the momentum of the sine wave? Well, there is no sine wave. It's been destroyed, right?
So it's like just becomes like rather than a wave, it just becomes like just a line, kind of, or
Yeah. Uh, do you know what a Fourier transform is?
Fourier transform. I've heard the word. Why do I? Oh, it's like the. I think I learned about this in calc too. It's related to like sine
Yeah.
and cosine waves. I'm trying to.
Yeah.
This was like a last minute thing that we covered at the last second, but
It's basically you're looking at a graph that's like amplitude and time,
yep,
and you see the sine wave.
yep,
And if you add a bunch of sine waves together, that's a superposition.
yep. Oh yeah, and then you can make just about any sort of
And you add,
if you can make just about any sort of shape with that, right? Like by
yeah, and
adding
but
the sine waves enough, and yeah, okay, keep going. Sorry.
yeah, okay, no, but 100%. So you make a sine wave. So you got amplitude over time, and you want it to be just for a blip of time. So you add a bunch of sine waves until the picture you get is just a single thing in time. It's like a single blip. That's where it is
Yeah.
in time. But because you had to add so many different waves to make that picture, the Fourier transform turns the graph kind of so that you're looking at amplitude and frequency. And those frequencies are all the different waves you added together. And that graph will be like the waves that are at 0, the waves that are at 1, micrometer, the ones that are 2, the different frequencies you've added. Now, like, if you've piled them all up and thought about them 3D, when you did the time thing. When you made that way, add them all together, put one behind the other, right? So you get your sine wave that you want to make. You put one wave right behind the other, until it makes that one that blips. You turn that sideways, and you got thousands of little blips of frequencies. So then you say, well, what's the frequency of the wave that you just created in that one moment of time? You can't know what it is because it's made of many frequencies. That's uncertainty. It's the same as sound waves. If someone holds a musical note for 5 seconds, it's not one sound, like they have to continue the motion. So it's a bunch of sound coming at you. And so because you get this expanded amount of time, you get this kind of know the frequency. But like, what is the note of a clap? It's so small in time that it doesn't really have like frequency to it. So it's like, if you knew what one was, in one sense, you can't know what the other is. Like the two things, waves have frequency and time, and they affect each other. If you look at it from one part of the graph, you get one picture. You look at it from its side, you get a different picture.
Yeah.
And it's like, that's what uncertainty is. You change the perspective you're looking at the thing, and you're going to see a different result.
All right. I think that's starting to make sense. So like,
I can send another picture for that. There's a really good image for that. Actually, I still have it probably on my.
Yeah, actually, you might be able to message me on Discord, and I can show it and look at it for the.
Yeah, there's the one. You get that?
I'll check. Oh, yep. Let me pull that up quick. Or does it not do that? There we go. All right, walk me through what this is saying.
Okay.
I see like the whole like when you turn it sideways, it just becomes like one sort of thing. Yeah.
Yeah. So if you look at like the three axes and the sine waves,
Yep.
they're progressing in frequency. So one is higher than the other, and it's going up the scale, right? So it's like, if you were to add those two together, they're at different frequencies, so they're at different levels. But if you just looked at it flat on, you see them on one two-dimensional plane. You add them together and you get that extra guy. Yes. But if you turn the picture sideways, you just see the sine waves straight on, which say that there's two frequencies.
So then, from the side view, that's like knowing the position of the particle.
Yeah.
And then from the other way from the other side, the time domain one, that would be like knowing the momentum of the particle.
Yeah. And so like you shoot it from its cannon, and you shoot it at a certain speed, so you know the momentum. Yeah. But by the time you detect it at the back wall, the perspective has shifted, and now you're just looking at not how fast it was going, but where it landed. So you can't say what was the momentum at the moment it landed, because the momentum was absorbed and turned into a position. And so you flip the picture.
All right. Yeah, I think that makes more sense, I think. So, yeah, all right, for sure.
Okay, you have to edit that in for people.
Yeah, it should be. I think it just popped up. It should be. Like, I just switched over, and because the OBS, I have like a full screen sort of thing for you, and then, for Hangouts, and then, so yeah, they'll see it on your picture.
Okay.
Yeah.
Okay.
Do I have anything else? I have a bunch of stuff written down, and I don't remember the context that I wrote all this stuff down in. I've written down relativity question mark, speed of light same for all observers question mark, and that I guess. Oh yeah, because I think I watched one of your videos, and that I guess I don't know. The principle of relativity doesn't make a lot of sense to me, so I don't know.
Okay.
So like,
Okay.
how
Well,
can I guess how can you be like traveling at a certain speed and like a faster speed, and then the speed of light be the exact same from your perspective as it is from a perspective of standing still, or is that
all
not
right.
a misinterpretation?
Well, I'm gonna start wrapping this up. So I'm gonna wrap it up with this, and I'm gonna also not give you that much either because I got a video coming out on that.
All right,
So, so I'm gonna make your viewers do some work and have to come to my channel for the answer.
all right,
Um, but just overall, it comes down to the concept of simultaneity. And again, this goes right back to classical stuff. It's not just about like it's not just in relativity that the the principle like the principle of relativity is classical. Special relativity is just plus light.
yeah.
And so
Oh, you're cutting out.
uh, it comes down to is good. It comes down
Yep.
to simultaneity. So if you are standing between two flashing lights, the amount of time it takes for the light to travel is going to be the same in both directions, right? Coming this way and coming this way, it travels the speed of light. So if the objects that are blinking are equal distance away from you, then you see them at the same time. And you can say, I simultaneously saw light from A and light from B, hit my retina at the exact same time. Special, but if you still in like the classical position, if you were on a train passing by those two blinking lights, the amount of distance the first light has to travel is being reduced as you travel towards it. And the distance the
Yeah.
object that you're moving away from is being increased. So, but it's traveling at the speed.
Oh.
So eventually you will still see both objects. Good?
Yep.
So yeah, so eventually you see both, you still see both lights, but not simultaneously. So now we have a principle of relativity that two different people saw two different events happening at two different times. One says they happen at the same time. One says, nope, they blinked at different times. Who's the correct observer, the one moving or the one standing still? It depends on your frame of reference and where those blinking lights are.
Yep.
All right. And what that does essentially for Einstein is he says the laws of Newton always hold and the laws of Maxwell always hold. But that means then that you cannot add Maxwell to Newton. Because in Newton, if you were on a train and you have a ball and you're moving at 100 kilometers an hour on the train and you throw the ball at 50, the ball's now moving at 150. But if you shine light on that train, the light continues to travel at the same speed. And so what Einstein was really doing was preventing there being a conflict from Maxwell's equations in motion. Because if you were to tie Maxwell's equations to Newton's equations just without Einstein, you would find that things don't work anymore. And so it'd be like saying, but that was a contradiction already, like known to the world, because they had trains. That's why his examples involved trains. And on those trains were lights that were wired in. And the lights still shot light to the front of the train as quickly as they shot to the back of the train. So the lights traveled at the same speed, but it was in motion. But this isn't, things in motion don't work that way. So he was actually preventing there being a conflict between Newton and Maxwell.
Oh. Huh. So basically, like, I guess under Newton, you'd expect the ones that are going to the back of the train to get there slower than the ones going, or hold up.
They get to the back of the train faster because the back of the train is approaching.
Yep. Sorry.
Yeah.
They get to the back of the train faster, and the front of it, it would take longer. Yeah, because the train is.
Yeah, which would mean that electromagnetism stops working the moment you start walking. But we're on Earth, which is spinning in a solar system, which is, spinning around a galaxy, which is a galaxy moving through space. So it's like, we're clearly always moving. So electrodynamics have to work in motion. And so you have to incorporate just this. It's just a reference frame where you hold light, the speed of light, for both, like for everyone. And it's just that when you shift from one person's frame to another, you have to keep those the same. And when you do that, you get weird things like time dilation and length contraction. But those are things that we do physically observe, like the muon.
Yeah. So like, I guess if you're like going faster, time is different for you, or time goes faster or
Yeah.
slower. One of
So
the
like
two.
the best example we have is the muon, because it's one of those cosmic rays, but it can't get very far into our atmosphere. It instantly bumps into things and kind of gets absorbed. And it just kind of it decays before it reaches the Earth. But the thing is, it reaches the Earth all the time. Like, so from our point of view, when we do the math without relativity, the time it takes for it to decay is like 2 seconds. But
Yeah.
because it's moving close to the speed of light, from its point of view, although it's still got like 2 second decay rate, its 2 seconds are longer. So it in its 2 seconds, it reaches the Earth. But from our point of view, going nothing close to the speed of light, we think that it should have decayed, hundreds of kilometers up. But it makes it all the way to us because we have two different reference frames for time. I think one of the best physical ways to think about like time dilation and length contraction, especially length contraction, is if you and I, like, you think one person gets smaller, that the other person should get larger in length contraction, but to both people just get smaller, right? So if I pass by you, you would see me shrink, but because you look like you're going the opposite direction to me, you shrink in that direction, and so we both see each other getting smaller. I think the best physical example of that is if you and I start walking away from each other, I see
Yeah.
you as getting smaller. You don't
Yeah.
see me as getting larger, though, because we're both seeing the same dilation in a sense. The one has to do with how fast you're going to the speed of light, and one has to go with like perceptual abilities over distance. But it's the same kind of principle where we both see each other not as one getting bigger, one getting smaller, but both getting smaller. Both of our times get smaller. Like the muon also thinks that it takes us a lot longer to do things, or that like we're supposed to be finished doing things a lot quicker, but we're not. Like, if it could think that.
Oh, you're
Up
cutting
here.
out.
Oh, I said I'm going to start wrapping it up here.
All right, for sure. Yeah, I think there's a lot of
I gotta go eat some supper.
yeah. Oh yeah, same. It's
Yeah, we
5:30.
got the same time.
Yeah, we got the same time zone. You're like the first person who I've talked to that has the same exact time zone as me.
I was
It's
worried about
crazy.
that because we don't do daylight savings, so it's like I don't know when people are in what time zone, and
Yeah,
even if they're in
yeah.
the same one as me, like straight down, it's like I don't know if we're in
Mm-hmm.
daylight savings or not. But yeah, let's go eat some food.
Yeah, let's go eat some food. And you all at home, go get some food as well. Go
Whatever
get
time
some.
it is. I don't care.
Yeah, whatever time it is. If it's midnight,
That's what
go get some
capitalism's
food.
about.
What?
That's what capitalism's all about: getting food at whatever time you want.
Yeah, yeah. You can go to the store whenever. Those 24/7 open stores. Those. It's just
You don't even
capitalism,
have to
baby.
wait in the bread line no more because you can
For
use
real.
this stuff checkout.
Yeah,
All right.
yeah, yeah. Automation ends bread lines. There we go.
Yeah, there you go. Perfect.
Perfect. All right, and then thanks all for watching, and I hope to see you all in the next video. Peace.